Welcome everyone back to this lecture series about compilers. And today we're going to learn about how to write an interpreter for the untyped lambda calculus. And that means that you will also learn how to use the concept of closure. And today I'm going to show you some OCaml examples that you can find under GitHub, David Broman, and OCaml examples. And there are many examples here. The ones that I'm going to show you now is available here as well, so you can just download the files and play around. I will show you how to implement the lambda calculus on top of an expression language so that you can have arbitrary arithmetic expressions, let bindings, and lambdas. So I've just copied over the other project, that is the arithmetic example. In this project, you can run programs like this, arithmetic expressions. You can also have bindings here, so that you can say like this, give it the name x and then multiply it afterwards, and run that as well. This all works, and you can try it out. So here you see also that we have name bindings. We introduced environments in the previous video. So if you didn't watch that video, I would recommend to check that out first. But we also want to write now functions. So we want to write something like this. We want to be able to have a lambda, and a lambda is an anonymous function. So you have a lambda here with a identifier. So that would be the variable for the parameter. And then you have the body of it. So say that, for example, you can write something like this, x times 2. And since it's anonymous, you can just apply it to a value, say 5. To do that, we need to extend the lexer, the parser, the AST. So let's start with the lexer. So we now need to introduce a lambda. So you saw in my example here, test, that I called it lamb. You can call it whatever, but I think it looks nice with a lamb. Lamb equals 2. And then we need to match here for this string and then provide it as a token. And since this is using men here, the token is defined in the parser. So we go to the parser file. Maybe we want to provide that here. So token lamb. We also want to provide a dot. In the example, we have this dot here. We don't have that in the lexi yet. Let's just provide it here somewhere. Well, like this, dot, call it dot. And then we go to the parser again, under F parentheses here, token dot. And this is men here that we can now later use this acronym dot here in the parsers to make it a bit clearer. We now also want to extend the ASTs, and then we want to have a lambda. So why not call it elam of? A lambda has a name string here, and it's got an expression. These are the two things in the untyped lambda calculus. If you have a typed lambda calculus, you will provide a type here as well. This is a simple interpreter, so we're just using a string for the name, but typically you want to change that to something else. One common way of doing it is the Brown indices, where you have numbers instead for indicating the names. But I will not do that now because it's a little bit simpler to just use names. And then you need to write the pretty printer. We have a lambda and x and e s print. And you can write this in many different ways. Now I'm just providing it simply like this. Parser. We have different productions here, and now you have to be a little bit careful here. It depends on what precedence you want for different things. We just write lamb. So now we have the token lamb first, and then as you can do in men here, you give it a name. So we basically match for the identifier, but we give it the name ID so we can use it later on. Then it should come a dot, and then we should have the let expression. So we are recursively getting the expression. And then we just provide code for it, elam IDE. So that's the implementation of the whole parsing of the lambda expressions. We're just ignoring here. If we get something here that we haven't done, fail with to do. And then we'll remove this one in the end. So let's see what happens if we just run this now. Compiled, and it parsed x, you see here, x times 2, and we have the lambda. That works very well, but we have the to do because we haven't implemented the actual evaluation yet. But what should we do here? We want to actually apply this lambda to something like this. So we apply the lambda to 4 here. And then the 4 will be substituted in the x here. So it should be multiplied by 2. So this should result in 8. Let's remove the let here. And the question here is a little bit about precedence. And we can just follow how OCaml is doing it. So we just make our interpreter similar and our parsing strategy is similar to OCaml. Just fire up a small test program here. Let x equals 2. We also have two functions, two lambdas. So in OCaml you write fun instead of lamb, x plus y. If we would do 3 and 4 here, and it turns out that OCaml use left associativity here. So it should be left associative, the application, but you don't have to write out the parentheses. Print f, printf. So we have a small program, OCaml build t.native, and we execute this program. And it turns out to be 7. So 3 plus 4 is 7. But what is the precedence level between this function application and an operator, like plus 5 here, or plus 10? What does that mean? Will it first do 4 plus 10 and then apply that? Or like if we write like this? Or would it apply 3 and 4 to this function first and then add 10? Let's run this and see what happens. Well, it actually took this 3 and 4, applied that, and then added 10. What does that mean? Well, it means that the function application has higher precedence than these ordinary operations like plus. We need to go to the AST and add the abstract syntax, eapp. It's got two expressions. And then we need to pretty print it, eapp, e1, e2. Want to pretty just copy this one. We write eapp instead. And then we have no x here, but we have two expressions, right? E1 and remove the x. And then we have a pretty print eapp. Then we want to create the parser. So we have implemented the lambda. We now want to have the actual function applications to have higher precedence than, for example, plus in here. And that's why we will create a new term here that is below in the ladder. We call that left because we will do a left recursion here. We also want to have some more extra terms that are even higher precedence than the left application. So we call that atom. So let's move, for example, the int down to atom. And we can also move the variable part down to atom and also the parentheses down to atom. But we also need a binding between expression down to the left. So we get the ladder. So that's why we create another one here. And we just write e left and then e. So that means that if it's not a binary operator, it will go down to this one. So now by doing this function application here that we define here in left, will have a higher precedence than the plus and minus and so forth. So how do we create that? Well, we need to say that the left operator is also an atom. So we need to connect that to the atom down here. And that is simply doing like this again. And then here comes the left recursion. So we have left. So we're doing left recursion. And to the right, we have atom. So by doing this, we get left recursion, which means that it will be left associative, which is what we wanted. And this is actually a bit tricky to get right if you haven't done it before, but now I'm just showing the recipe and then it will work. So we give names to E1 and E2 so that we now can construct the application eapp, E1, and E2, like this. What we can do is to see if the pretty printer is working. We had the lambda and the application now with a 4. Still, we haven't been able to evaluate anything, so we have this to do here. But what we can see here is that we have a lambda, and around it we have the app. So it actually worked for the first time here. And now we can write a program that is more complicated if we want to. We can run like lambda y, and we have x multiplied by y instead, and 4 and 7. So now you see we have two arguments here, x and y multiplied together. So this is actually parsed like this. First we apply the 4 and then the 7. And here we see that we eapp 2 times. And then we have the lambda. And here we have the two arguments, 4 and 7. But let's actually create the evaluator, because that was the purpose. And to do that, we need to move to the eval function. The first thing we need to add is, of course, what to do with the lambda, elam. What should that evaluate into? The problem is that if we just provide the lambda as a value, we will not get the right environment, because we will get the environment from the function that is called. But we want to actually to save this environment. And to do that, we introduce something is called closure, which means that we keep the lambda, but we also store the environment that is currently here right now when we come to a lambda. And the closure is a term that we don't have any syntax for it because it's constructed during evaluation, but we still add it to the AST. So let's go to the AST and we can call it eClose of the same thing as in the lambda. We want to store the name, we want to store the expression, but one thing more, we want to store an environment. So now we have the environment, and this is the same environment that we had before when we were using the lets. So that is the binding of a name to a value. So now we actually have to create that type here because we will use it here. Call it env equals to, and then it's a tuple, string, star, expression. So we have a binding between the string name and the value. There's just some expressions that are values. And this is a list. So this is the associative list that I talked about in the previous video. As you can see here, expression here refers to this expression. An environment here refers to this environment. So we have like a mutual recursion between these types. That is allowed, but we need to then change this to an and. So that kind of combines together this type to this one. And now we can have this mutual recursion. We also need to pretty print it as always. We have X and E. We can actually ignore the environment. We don't pretty print it now because it's a little bit too much work and I'm feeling a bit lazy. Closure is actually the same structure as the lambda. So we just copy that and then we can pretty print this in the same way. So now we have the pretty printer for the evaluator. Let's go over to actually write the rest of the interpreter or the evaluator. So we just translate the lambda to a closure, close like this, and then we just copy it over. But which environment should we have? The lambda does not have an environment. Well, when the evaluator comes here, the environment is always provided in the evaluate function itself as a parameter. So we just take this environment and stick it into the closure. And this is actually why it's called a closure, is this, we have the combination of a value and the environment. So let's see what we should do with the application. We have an e-app, and it's got an E1 and an E2, so two expressions. But these are expressions now, so they have not been evaluated yet, which is in a call by value language. We evaluate first E1 and then evaluate E2, and after that, we actually apply the function. So that means that this must evaluate to a closure, since this will be a lambda that becomes then a closure. And then we can call it, but this needs to be a value. And in our very small, simple language, there are two things that can be a value. That is a integer, and it's also the lambda that is converted to a closure. That's how we can send a function to another function. We match, but we evaluate first. We evaluate like eval, env, e1, eval, env, e2. So we evaluate them, and this means that e1 will be evaluated before e2 with, so then we have we will match, and then hopefully this first part becomes a closure. So then we just say that, oh, it became a closure. And we have then, and then we also call it another name because we want to separate this environment from the environment that is inside this closure. So if we get that one, then this should be a value. And I mean, a v is nothing magic, but it will be an integer or another closure, but we don't know and we don't care. So we can just take that one. So basically, we want to stick the value that we just computed here onto the new environment. We just do eval again recursively, and then we have the environment, but we should have the environment too. So why E? Well, it's the thing that is inside the closure we should execute and continue to evaluate. This E, right? The v is what we're going to provide and put on the environment. Since we're now calling this function, we just stick on top the value to the environment. We do that by binding x, which was the name of the closure, and v, which is the new value, which is the thing that we're applying to. And then we stick that to the environment by consing it. We're binding in the same way that we did for the lets, but also for the lambdas. And it all becomes correct because we have these environments. An alternative to closures is to use substitution, which is typically used in small step operational semantics, which is semantically as good, but it's typically implementation becomes much slower. This was if everything went well, but it can go wrong. We just catch all here and say that we fail incorrect application. So that's the e-app. We are evaluating both the E1 and E2. We hope that the first thing becomes a closure, and then we have the value for the argument, and we continue by evaluating again the E inside the closure, and then stick on the environment, that is, we take the closure environment and put on the binding between the X and V. What is left? Well, if we go to the AST here, we see that one thing is left. It's the closure that we introduced, right? So we have also a closure. And what should we do with the closure? Well, that's just a value. So we just write eClosure XEN. And it varies to eClose XEN. If everything is correct now, we can remove the to-do. So let's see if it works. And it does. Wow, no errors. If we go to the example again, took this 4 and 7 and applied this to these two lambdas and then multiplied together, and that became 28. So we have now an interpreter that can interpret lambdas and lambda application. The nice thing is that we can combine this with lets, where we have here an example. We have foo, gave it a name. So we are giving the lambdas here names. So that is basically a function definition, right? So we have two parameters, f and x. So f, by the name, we can maybe suspect that this is actually a function. And well, it is, because what we do here is we take x here, multiply it by 2, and then the result of this we apply to f, which is a function. But that function is sent to foo as an argument. And we see here down here that we do this. We call foo with bar, which is another function, and with 3. And you see here bar is defined as a function where we're adding x plus 10. So here is a lot of things are going on, but the cool thing is that it all works with this small extension. So let's run that, and it becomes 16. So that's what I wanted to talk about today. I hope you learned something. Maybe in the future, I will also provide a video that shows how to do recursion and if expressions so you can write more complicated programs. And maybe we'll also add some types to it. Thank you. If you like this video, please subscribe and add a comment and tell me more about what you want to learn about compilers and programming languages.